Okay, welcome everyone to this fifth edition or fifth season, as we say, of the One Word ABC. My name is Umberto Bikini. I'm streaming from Gothenburg in Sweden, and today's speaker is the first speaker of this fifth season is Carlo Albert from. Is based at Swiss Federal Institute of Aquatic Science and Technology, if I'm correct, if I'm looking at the right page.
Yes.
And he's the head of the group of mathematical methods in environmental research. And if you see him from his webpage, he has, of course, interest in Bayesian data sciences and, of course, modeling of environmental systems. So today's talk is about learning of summary statistics for Bayesian inference with autoencoders. Well, thanks a lot, Carlo, for accepting to be with us, and feel free to start sharing your slides.
Thank you very much for the invitation. I start sharing. So you see screen plus mouse, right?
Yeah.
Yeah, all right. So welcome everyone. I would like to talk today about a recent method or a method that we suggested recently of how to use autoencoders to learn summary statistics for Bayesian inference. So let me start with the problem setting. I think to this audience, I don't have to explain this in great detail. We're dealing with inference problems with intractable likelihood functions, and this is typically the case for one of these two reasons. Either we have a large number of unobserved latent variables x, which we need to integrate over to get to the likelihood function, or we might have an unknown partition function or normalization factor if you think of an Ising type model where we just specify the couplings between the parameters and the observations. And so if you want to do inference with such kinds of models, we would like to avoid calculating these integrals. And as you all know, ABC is one of the methods that we can use if we, let's say, if we're really only just interested in doing inference about a small set of parameters and we're not interested in inferring all the latent variables as well. So in such cases, we can just do inference based on forward simulations and then compare these forward simulations with the observations in terms of some features or summary statistics, which hopefully capture most of the information about the parameters. And so there's two important quantities that have to be dealt with. One is obviously the choice of these features or summary statistics, and the other one is the tolerance that we are allowed to accept between simulations and observations. And these are also the two quantities that justify the A in ABC, the approximate. Typically, we have to end up with a finite tolerance, and typically we're using summary statistics that do not capture completely the information about the parameters. So here's a simple example. The Ising model, of course, it's a member of the exponential family, and we can, it is manifest here that all we ever need to know about these simulations is energy and magnetization if you want to infer temperature and magnetic field. So these are called sufficient statistics, but typically we will not be able to find sufficient statistics in real applications. So in this talk, I want to focus on the first problem of how to find good summary statistics. But before I do that, I would still like to advertise a little bit the other thing. So how to find a good tolerance. We've suggested an algorithm some time ago, which combines approximate Bayes computation with simulated annealing. We call this SABC these days. And the idea basically is that we sample from this object here, so the joint prior of summary statistics and parameters times such a Boltzmann factor, which is e to the minus distance measure between simulated and observed summary statistics. divided by a temperature. And so we keep sampling from this quantity while at the same time gradually lowering the temperature. And as you can see, if the temperature is large at the beginning, we're sampling from the prior, and as it converges to 0, this converges to delta function. So we end up with a sample from the posterior. So here in this box is a way that can be done in a sequential manner. But there's of course also parallel versions of that. And we can show that as long as we lower the temperature slowly enough with respect to some power law, we can guarantee convergence. But in practice, we always use adaptive versions where we lower the temperature in a way as to minimize entropy production, so that it's a quantity that we are using for as a proxy for wasted computation. So I see there's questions popping up in the chat. I don't know, Umberto, are you taking care of that? Or
yeah, it was just me saying, everyone, please write here if you want.
Okay. Good, fine. All right, so that's just a little advertisement slide for our SABC algorithm. But now I would like to focus on the actual topic of today's talk, and that is finding summary statistics. So in a broader context, that's a data compression problem. So if you want to lower the tolerance, the computational price grows exponentially with the number of dimensions, because you want to match each of the particular summary statistics at the same time. So we have to try to compress the information in the data that is relevant for parameter inference into few statistics, and generally that leads to a loss of information. And so this is the trade-off here that we are dealing with, the trade-off between accuracy of the posterior and efficiency of the algorithm. So let's formalize this a little bit. So let's consider a generic stochastic model for some outputs y conditional on some parameters theta. Typically, we have few parameters, so p is rather low, and typically we have large dimensional outputs like time series or fields or whatnot, so n is typically large. And then we have a summary statistic, which is simply a map from the output space onto some lower dimensional space, RQ. Again, Q is typically small, of the order of the number of parameters. And now we have this trade-off here. We want our summary statistics to be both accurate and efficient. And I think an appropriate way of formalizing these things is using information theoretic concept. So we want them to be ideally sufficient, that can be expressed information theoretically using the mutual information. So we want the mutual information between the summary statistics, which are a function of the outputs, and the parameters to be as large as, or we want in the sum to have as much information about the parameters in the summary statistics as the whole data set has. So if, without this 1/n term, that would express exact sufficiency. In practice, that's typically too much to ask for, so we relax this condition to what we call asymptotic sufficiency. So we are happy if we get most of the information of the parameters, and most in terms of 1/n terms as the data set grows. So that's again an accurate posterior, and also the efficiency can be formulated in information theoretic quantities. Typically people say we want just few summary statistics, but I think the number of some summary statistics is not so telling. You can always add, correlated summary statistics, and that doesn't really deteriorate the efficiency of the algorithm. At the same time, you might have only few summary statistics, but they're very noisy, and that also hampers the convergence. So I think rather than speaking of the number of summary statistics, we should speak about the concentration of the summary statistics. So ideally, we would like, for fixed parameters, we would like the summary statistics to be almost point-like, so very much concentrated. That is the same as to say that we don't want summary statistics to encode noise. So they should encode almost all the parameter information, but ideally none of the noise. So here, again, we can formulate this asymptotically. We would like the conditional entropy of the summary statistics conditional on the parameters to go to minus infinity, like a logarithm of n. So that's just from the central limit theorem. If we assume that summary statistics are some sort of average, which they typically are, then they should go to minus infinity like that. So these two quantities really, in a way, allow us to interpret summary statistics as thermodynamic state variables. It's pretty much the same thing. If you think of the Ising model, it is, you can either describe your system by, say, temperature and magnetic field, intensive quantities, or you might describe it by energy and magnetization, extensive quantities. And these amount to this almost to the same thing that's called the equivalence of ensembles in physics. And it's just an expression of this concentration property. So if we fix temperature and magnetization and energy and if we fix temperature and magnetic field, and energy and magnetization are very much concentrated, and it's, we can describe the system by either of the two sets of variables. All right, so that's the setting. That's what we would like to achieve. And now, obviously, a good choice or an obvious choice for summary statistics is just to use parameter estimators, because by their very design, they contain a lot of information about the parameters, and they're also ideally very well concentrated. And that's what has been done in the literature quite a lot. So you can use any type of parameter estimator. For instance, you can use the posterior mean, and then obviously we don't know that, but we can use some form of regression starting from a rich initial sample from the prior, which you need anyway at the beginning. You can make some form of regression and try and approximate this posterior mean, and then use that as summary statistics. And I mean, in this famous paper by Farnhad and Prangel, they did exactly that, using linear regression. And this is also something that we have incorporated in our SABC software packages. Linear regression has gone a bit out of fashion lately, and people use all sorts of machine learning models to do the same thing. So there's many papers that go in this direction. I'm just citing here one from Young 2017, where they use some form of neural networks to basically do the same thing. So that's fine as long as you have a large set of IID data points. Then parameter estimators pretty much capture all the information you need to do inference. But that's no longer true if your data is correlated, and that's due to an energy entropy trade-off. So if you and that's prevalent if you have a large number of data points. If they're correlated, often the system doesn't behave in the most likely way, if you will, but in the most common way. So if you have many realizations that can the number of particular realizations that belong to a certain set of summary statistics can sometimes overrule the energy. I will show an example in a moment. So for the exponential family, this can be made manifest. We can write down what in physics is called the free energy, so the minus log of the likelihood function of the summary statistics given the parameters. And if you plug it in, this naturally splits into an energy term and a entropy term. Energy term depends on the parameters, entropy term does not. The energy term basically just measures the likelihood of a model realization for a given set of summary statistics, whereas the entropy counts, if you will, the number of model realizations that lead to a particular set of summary statistics. And these two can be at odds with each other and lead to multimodal free energy landscapes. That simply means that even for fixed parameters, the model can behave in different types of ways. And for the purpose of Bayesian inference, it is important to keep track of which type of realization the model makes, because that can lead to very different posteriors. So these different types of model behavior can even persist in the limit as n goes to infinity, and that's what then is called the different phases in physics. So I have a little toy example just to show that this is not just something that happens in statistical mechanics models, but is more generic. So here's a little toy, which is an iterative and an autoregressive nonlinear map. So our data set is a time series y, and yn plus 1 is given by alpha times some nonlinear function of yn plus some noise, IID noise. And the parameters of this model are simply alpha and sigma. And for the nonlinear function here, we assume here such a single-humped function, which admits two stable fixed point, one at 0 and one up here. And now, depending on the choice of the initial condition and the choice of the parameters, it can happen that even for fixed parameters, sometimes the model realization goes down to this fixed point and sometimes it goes up to this fixed point. That's exactly that energy entropy trade-off, right? One of the two is the energetically favored one. That's the realization that you get if you set the noise to 0, because the noise 0 values are the most likely values. But for purely entropic reasons, sometimes the system might prefer to go to the other one, simply because there's many more microscopic realizations that lead to the other attractor. So you can have this bimodal type of behavior. This is important to take into account when doing Bayesian inference with such a kind of model. So of course, this is a very simple model and we have full control over everything. It's a member of the exponential family. So we can explicitly write down a set of sufficient summary statistics. Here is one convenient parameterization of a set of sufficient summary statistics. And you immediately realize, if you write down through the math, that although we only have two parameters here, alpha and sigma, we need 3 summary statistics to reach sufficiency. And one way of parameterizing them is the following. So you can just use parameter estimators, maximum likelihood estimators for alpha, which basically uses some autocorrelation to estimate alpha, and the sigma, which is just the sum of squared residuals. But then you need another one, and the role of this other one is exactly that. It is to distinguish the different type of model behaviors that you can have even for fixed parameters. So we call this an order parameter, which tells the two different types of model behavior apart. So if you plot these 3 summary statistics, so this is the prior distribution of the 3 summary statistics that we plotted here. We have on the X and Y plane, we have the parameter estimators alpha hat and sigma hat, and on the Y axis, we have the order parameter. And you see, you get these 2 overlapping quasi 2-dimensional manifolds. And here in the middle, that's the interesting part. That is where these 2 overlap. So that's where you can, for a fixed set of parameters, you can have either be in the lower attractor or in the upper attractor, and the order parameter will tell you these 2 behaviors apart. If you're away from this area of coexistence, then the third the order parameter is pretty much just a function of the other two and doesn't carry any additional information, and you might as well omit it when doing your inference. But if you encode, if you're in this area of coexistence of different model behaviors, you need to have the order parameters part of your set of summary statistics, because you need to know in which type of model behavior you have. And so obviously, if you have this situation, you will not be happy with simply parameter estimators, because you need more than that. You need this additional information as well. And in order to cope with that, we suggested this type of machine learning architecture, which is a sort of an autoencoder architecture to learn sets of summary statistics that are not necessarily bounded by the dimension of the parameter space that you have. So how does this work? We have our model here, which would be, for instance, our nonlinear AR1 model before. You can always write that as a deterministic function of some model parameters and some bare noise. So bare meaning it doesn't depend on the parameters. That would be the epsilons in the previous example. And then the model generates an output. So let's say a time series Y. Then we have an encoder here, which is some form of neural network, convolutional neural network, for instance, the job of which is to learn the summary statistics. So it compresses the output into summary statistics. And then you have a decoder, which then tries to reconstruct the model output y hat using the summary statistics, but then we give it a cheat, we give it information, we give it the noise that we have actually used to generate that particular data set, which we typically have available when we write our model M ourselves. And so since the decoder has access to the exact noise that has been used to generate the data, it creates an incentive for the encoder to encode all the information in the output that is not noise. And that's precisely what we want. We want the encoder to encode all the information that is coming from the parameters and is not coming from the noise. So we realized that it's also a good idea to use regularization. So our loss function would be, on the one hand, say a loss function for the generated output y hat. But then we realized it's also a good idea to say that, here this bottleneck has dimension q, and q is a bit larger than p, so the number of parameters. So we use the first p slots here as parameter estimators. And we let the remaining slots we let free, and the encoder can use it for whatever it deems good. Yes, so that's basically it, and the hope is that then the encoder uses these extra slots to encode this type of order parameters that we might need to tell different model behaviors apart. So we call this the explicit noise conditional autoencoder, because we give explicit noise realizations to the decoder. We might not always be in that situation that we can extract the bare noise from our model generator. Sometimes we just have a black box simulator and we don't have access to the bare noise, or the bare noise might be too high dimensional. So we also came up with an implicit, this is wrong. This should be saying implicit noise conditional autoencoder. And here we give information about the noise by simply making several replica of model outputs. So for each set of parameters, we make several different replica of model outputs, and the variation of these replica then conveys some noise information to the decoder. Encoder learns summary statistics for each of these replica. Again, we use a regularization. We say that the first p slots of these summary statistics should be parameter estimators. And then the decoder, in this case, tries to come up with the best parameter estimator it can. So because here the first P slots are already parameter estimators, what the decoder tries to do is to find the right weighting between these different parameter estimators. And again, this is precisely how it creates an incentive to the encoder to use these extra slots to encode extra information. Oops, somehow I made I wrote something here without noticing. So it creates an incentive to the encoder to use these extra slots to encode information about different type of model behaviors, because different type of model behaviors might have very different amount of information about the parameters. If you think back of our simple toy model, the AR1 model, if you go to the upper attractor, you have much more information about the alpha parameter than when you go to the lower attractor. So it's important to know which attractor you are in order to know which amount of information you can pack into your summary statistics. So this is turns out to work as well, not quite as well as an explicit autoencoder, but it does the job as well. So let's now look at the example. I don't know how to get rid of this. Do you see this red thing also?
Yes, I do.
I don't know how this appeared, but just, okay, now it's gone. So I see there's a question, maybe. No,
No,
okay.
no.
So we see who the culprit was. Okay. So okay, so this is now what we.
Actually, yes. Now there is a question.
Okay.
Is there any precise theorem about all that?
You mean these type of autoencoders? No, there's we're not at the level of precise theorems yet. Maybe I leave that to the statisticians to cast that into theorems, but no, we don't. All right, so this is what we get when we apply our autoencoders to this toy model. So here on the left, it's the same plot I've shown you before. So these are the exact sufficient summary statistics that we know of. And this is what our ENCA, the explicit noise autoencoder, spits out. And you see it realizes that it should use this third slot. So here we gave the bottleneck dimension 3. We said the first two should be parameter estimators, and with the third one you can do what you want. And it realizes that it should use this third quantity to distinguish between the two different types of model behavior in the area where we have coexistence of these two different types of model behavior. So that looks all right. And that's then confirmed here when we do the ABC inference. So here what you see first, the green one is the true posterior, which of course we know in this case. We know precisely what the likelihood function is. So we made an MCMC to get the true posterior. The red one, the big one, is what you get when you do inference only using maximum likelihood estimators, and you see we lose quite a bit of information about the alpha parameter because we don't know in which of the two attractors the data is. The blue one is the posterior, the approximate posterior that we get if we use the three statistics that have been learned by our autoencoder, and we see it's pretty close to the truth. So it does a pretty decent job in learning all the information that is relevant. And you see also what happens if we give them the autoencoder just two slots in the bottleneck, then we're somewhere in between the blue and the red one. It's not quite as bad as the red one, which is kind of interesting. So although we tell the bottleneck, okay, use these 2 slots to learn parameter estimators. It sort of overrules that to some extent, and it learns also some information about the separation of the 2 different attractors at the cost of making the 2 parameter estimators a little bit worse. But it's beneficial because the posteriors we get is better than the posterior we would get if we only use maximum likelihood estimators for inference. But it's not as good as what we get when we use 3 statistics. It's also nice to see what the decoder does. Of course, we can look at what the decoder does. So what we did here is after we have trained the network, we made some model realizations with our nonlinear AR1 model, and we had one model realization that went to the upper attractor and one model realization that went to the lower attractor. And the blue one is the reconstruction of the decoder using 3 statistics, and you see it's almost a perfect job. Remember that the decoder has the precise noise realizations at its disposal, so it pretty much learns the model, which is not very hard here for this model. So we used an LSTM here as a decoder. And you also see what happens if you only give it 2 statistics in the bottleneck. It still learns that it should go when it should go up and when it should go down. So this phase separation, it still learns, but it doesn't learn the parameters alpha and sigma quite as well. So it's off here and it has too little noise. So it has a little because it needs some of the information, these 2 slots, to learn the phase separation. It sacrifices a little bit of information about the parameters.
Carlo,
yeah,
there is a question by David Fraser.
mm-hmm.
How do you know the number of slots to add?
Yeah, that's a good question. Trial and error. Now we can. So there's different different things, different ways of what we can do. So one thing we tried is so we start with the number of parameters, q equals p, and then we go p plus 1, p plus 2, p plus 3. So we try several of these, and then we monitored how. So then we ran our ABC, and then we monitored how small the distance is in ABC or we got. So how close to the truth we got, and then we often see an optimum, right? If you have too few statistics, it's not so good. If you have too many statistics, it's also not so good, and we have a sweet spot somewhere in the middle, which we then deem to be a good number of summary statistics. But this is really just a very rough way of dealing with it. We have also tried to use some intrinsic dimension, so run it with a relatively large size of the bottleneck, and then see whether the learned statistics are confined to some submanifold of lower dimension. But we haven't explored that fully. So it's more or less a trial and error type of thing at the moment.
Thanks. And now that we're at the point of asking questions, there is a question by Peter. Mm-hmm. It's maybe a bit long if you want to check it yourself.
Yeah. Is the autoencoder trying to minimize the mean squared error between the input and output, or is it trying with another objective that maximizes the mutual information between parameter and summary statistics? So it's the first. So if we go back to this one, yeah, it's the mean squared error basically. So it's these 2 things. So we want the reconstruction of the model output to be good. So that's this part, and this is the regularization, if you will. We also say that the first p slots of the q slots should be a parameter estimator. So that's what we use. We don't use mutual information type of loss functions, but it might be an interesting avenue to pursue. Okay.
Okay.
Thanks for the question. All right, so, okay, what else do I have? Yeah, so we also did apply this to a little harder example of which is not part of the exponential family anymore, but it still does a good job. But I'm not going to show you this. There's another question. How much effort is required to train the autoencoder compared to the effort used to run the ABC? Yeah, that's also a good question. So it's more effort to train the autoencoder than to do the actual ABC. I cannot fully quantify it because so far what we did is basically just to show that in principle it works. So we ran both the training of the autoencoder and the ABC ad nauseam to really make sure we have convergence to show that the things work. And there, the training was the harder bit. But in practical applications, where we have not yet much not much experience, it has still yet to show up what is how it works out in practice. All right, so I'm not going to show you this other example. Just take my word for it that it also works in this example outside the exponential family that we have tried. But I want to show you another thing which is, I find, somewhat more interesting. Namely, we figured that we can apply this method also straight to real data and not just to model, to simulated data. Because all this autoencoder does, in a way, it disentangles high dimensional irrelevant information from low dimensional relevant information. So for the purpose of learning summary statistics, the high dimensional irrelevant information was the noise information in the model outputs, and the low dimensional relevant information was the parameter information in the outputs. And we figured we can maybe also apply that to real data, and we applied it to a hydrological data set. We applied it to the so-called CAMELS data set of the US. That's a large data set of around 600 something catchments with 30 years of data each. So we have, on the one hand, we have meteorological drivers, that is precipitation, temperature, and so on, time series. And on the other hand, we have river runoff that is also measured for 30 years for each of these catchments. And so here, instead of a model, we have Mother Nature, if you will, right? Mother Nature takes meteorological drivers, and it also takes catchment properties, right? So what's the soil type, how much forest is growing there, etc. And from that, it generates a model output, which would be a time series of river runoff. Now we want to do the same thing here. We want to disentangle these two types of information in the river runoff, and we want to see what are the fingerprints in time series of river runoff, fingerprints about catchment properties. So obviously the strongest drivers are rain. If you have a peak in the rain, there's a peak in the runoff. But we want to take all that away and see what's left. So what does the runoff tell us about soil type, if you will, or different types of catchment properties. So we applied the same type of autoencoder to this data set. So now the meteorological drivers play the role of the noise, and the catchment properties play the role of the parameters. Here we couldn't or didn't want to use a regularization term here because, first of all, we don't know which catchment properties are the important ones and how to quantify them really. So we just use this loss function here. And then we train our autoencoder on this data set, and we found something quite interesting. So first of all, we found that you only need something like 4 features to predict the stream flow or the river runoff very well. So it seems that apart from the meteorological information, rain, etc., there's only 4 additional features in the runoff that comes from the catchment properties. And we saw that also again by basically brute force. So we started with a large bottleneck of 27 features. 27 because also we have a list of real catchment properties, soil type, etc. It's also 27. So we figure we start with 27. Then we lowered it, and it didn't really get worse until we dropped to only 3 features. Then there was a larger drop. So it seems that we need about 4 features to encode all the information that is there. And we also see that we get better results at runoff prediction when we use our 4 features than when we use all the known catchment properties, which indicates that there's in this list of known catchment properties, there's still some information missing that we might want to have to predict stream flow accurately. Then we obviously wanted to also interpret these 4 features, and we saw that okay, there's some correlation with geography, so they're not just scattered randomly, but we have some, you know, some correlation with different topographical features. We also correlated them with the 27 known features, and we saw okay, they seem to encode certain type of information that can be interpreted. So one of them seemed to be correlated with altitude and snow, another one with a different type of vegetation. So we have some form of interpretation, but this is all still at the very beginning, and we're not yet at the point where we can ultimately conclude. All right, I think I am done here. Let me stop with this conclusion slide. So we have shown both with synthetic simulated data and real data that the ENCA, so this explicit noise encoding autoencoders, can be used to disentangle high dimensional irrelevant from low dimensional relevant information. We've seen, at least in some simple case studies, that the method can be used to learn summary statistics that are near sufficient and also very well concentrated. Yeah, and then we've seen this example here that we also can use to learn the autoencoder to learn catchment features in observed streamflow data. This is the QR code of our paper in SciPost Physics on this autoencoder if you're interested, and I would like to thank my collaborators, Simone Olsega, Antonietta Mira, Firat Özdemir, Fernando Perez Cruz, and my PhD student Alberto Bassi for collaboration on these projects. Thank you very much for your attention. I'm happy to take some more questions.
Thanks a lot, Carlo. Very, very interesting. And sure, we go now to the discussion session, but I'm going to stop the recording now.